Hey everyone, welcome back. In this video, we're going to apply the linear scheduling method, LSM, we learned earlier to a few example projects. Let's dive into our first example. In this scenario, you're managing a project to install 5,000 linear feet of underground utility pipe. The work involves several sequential activities: excavation, subbase preparation, pipe laying, compaction, and backfilling. Each activity has a specific production rate, which is provided in parentheses. For instance, the excavation crew can complete 500 feet per day, while the subbase team works at a slightly slower rate of 250 feet per day. These production rates will be used to determine the slopes of the activity lines when developing the linear schedule. Additionally, there's a project constraint related to distance buffering between activities. Each activity can only start once its predecessor has completed at least 500 feet of work. For example, the subbase team must wait until the excavation team has finished 500 feet before they can begin their work. With these factors in mind, let's go ahead and set up the linear schedule. First, let's set up a time-location diagram for our linear schedule. In this setup, time is represented on the horizontal axis in days, while location is shown on the vertical axis in feet, reaching a maximum of 5,000 feet. Each column represents a 2-day period, and each row corresponds to 500 feet of progress. Now, let's begin with the first activity, which is excavation. Since excavation progresses at a rate of 500 feet per day, completing the entire 5,000 feet will take 10 days. The activity starts at the origin point, where both time and location are 0, and its endpoint is at day 10 and 5,000 feet. Following excavation, the next step is the subbase activity, which moves at a slower pace of 250 feet per day. Because of this lower production rate, it will take 20 days to cover the 5,000 feet. Unlike excavation, the exact starting time of subbase cannot be determined immediately since it depends on the required distance buffer. To establish an initial schedule for this activity, we can begin by setting a tentative start date for subbase slightly after excavation begins. Suppose we start subbase 2 days after the first activity. If that were the case, the endpoint would then be at day 22 and 5,000 feet. Now, it's important to check whether the schedule meets the project constraints. Specifically, the minimum required distance buffer between activities must be 500 feet, which corresponds to 1 row on our diagram. This means that at any moment, the vertical space between excavation and subbase should not be smaller than this limit. Because subbase progresses at a slower rate than excavation, the distance buffer naturally increases over time. The smallest gap between the two occurs right when subbase begins. Looking at the chart, this initial buffer is actually 1,000 feet, which is larger than necessary and results in an unnecessarily long schedule. To avoid this inefficiency, we should try to start the subbase activity earlier. The best way to determine the optimal start time is to gradually shift the subbase line to the left, reducing the initial gap until it is exactly 500 feet. By doing this, we find that the subbase activity should begin 1 day after excavation, which means it will now be completed by day 21 instead of day 22. By making this adjustment, we ensure that the schedule remains efficient while still meeting the required distance buffer constraints. Now, let's move on to the third activity, which is laying pipes. This activity progresses at the same rate as the first activity, excavation, at 500 feet per day. Because of this, the slope and duration of its line on the schedule will be identical to excavation. To determine the correct positioning of the line for laying pipes, we need to ensure that the minimum distance buffer between this activity and its predecessor, subbase preparation, is exactly 500 feet. Since the subbase preparation progresses at a slower pace than pipe laying, the distance between these two activities gradually narrows as the project moves forward. Therefore, the minimum buffer will occur at the end of the subbase activity, where the gap is at its smallest. To meet the required buffer, we must shift the entire pipe laying line to the left until the minimum distance buffer is exactly 500 feet. After making this move, we determine that the pipe laying activity should start on day 12 and finish on day 22. Now, let's repeat the same process for the last 2 activities, which are compacting and backfilling. Since these are the fastest activities in the project, they have the steepest slope on the schedule. As a result, the minimum distance buffer for these activities will occur at the end of their respective predecessor. After applying the same method, we came up with this final schedule. One important note to keep in mind for this class: when drawing these linear activity lines, we will assume that activities can start at any point during the day. This means that when shifting an activity to meet the required distance or time buffer, you don't need to worry about aligning it with even time units. Simply position the lines wherever they satisfy the necessary constraints for both time and location. Alright, let's move on to the second example. In this case, you'll need to develop a linear schedule for a 15-station long road project based on the information provided, including activity sequence, production rates, and durations. Additionally, the minimum distance buffer for this project is set at 2 stations. This example is quite similar to the first one, with one key difference. we have two nonlinear activities, mobilization and box culvert. The mobilization activity takes place only at the starting location of the project, while the box culvert is fixed at Station 11. All other activities in this schedule are linear, and their production rates are provided as shown here. It's also important to note that the minimum distance buffer between any two activities is 2 stations, and the surveying activity can begin immediately after mobilization is completed. Since we will be applying the same method as in the first example, we won't go through the detailed step-by-step process again. Instead, we will review and discuss the final solution. This is the final linear schedule for example 2. Now, let's take a closer look at it. The first activity in the schedule is mobilization, which is classified as a bar activity since its location does not change. On the schedule, it appears as a horizontal bar positioned at Station 0. Another bar activity is the box culvert, which is located at Station 11. As mentioned earlier, for this class, it's acceptable to start activities in the middle of the day, like this activity. However, in real-world applications, you may want to adjust the start time to begin on the next full day. Now, let's check the distance buffer for some activities. For instance, the minimum distance buffer between surveying and clearing and grubbing is 2 stations, which meets the required constraint. Similarly, the minimum distance buffer between the box culvert and subbase is also 2 stations, ensuring that the buffer requirement is satisfied. Overall, this schedule appears to meet all the necessary constraints. Before we wrap up, make sure to go through this example on your own and try recreating the schedule. If you spot any errors or have any questions, feel free to let us know. Alright, that's it for this video. We applied the linear scheduling method, LSM, to develop linear schedules for 2 example projects. Thanks for watching, and we'll see you in the next video. Goodbye.